Hanie, I see you here in our room, and we have Hanie Sedghi, the Senior Research Scientist from Google Brain. Hanie, if you want to unclick and share your screen, and we will get started.
Hi, everyone. Do you see my screen okay?
Yes, it looks good, Hanie.
Awesome. Very excited to be here. It's been a while since I was last at MLconf, and it's always a pleasure to be here and with this amazing community. Today, I'm going to talk about our very recent work on exploring the limits of large-scale pre-training. So before that, I want to take a step back and talk a little bit about my general theme of research, which is understanding deep learning phenomena. Over the years, I've been working on principled approaches to theoretically and empirically investigate deep learning phenomena using tools from ML theory and statistics. And the goal is to understand when and why deep neural networks generalize, improve their training and generalization performance, in the state-of-the-art deep learning models, and also extend the current success of our models to new domains. And the reason I'm excited about this is our understanding of modern neural networks lags behind their practical successes. And this growing gap poses a challenge to the pace of progress. And although there's been some progress in this area, still we're far from answering many fundamental questions, such as generalization capabilities of deep models and how to ensure successful transfers to new domains. And I believe this understanding helps us extend beyond our current use of deep learning in a reliable way. So with that, let's focus on a specific topic at hand today. And the prelude I wanted to do is that there's been impressive progress recently on transfer and few-shot learning that has been achieved by scaling up model and data size. And prominent examples are GPT-3, which is an image, it's a large transformer model trained on a large corpus of data. Also CLIP, which is a pair of image encoder and text decoder models that are trained with the contrastive loss on 400 million image text samples from internet, and they've been showing a lot of interesting capabilities. And also, there's been some work on showing that massive data sets, such as Instagram images and Google's JFD 300 million data set, have essentially helped getting much better performance on our models. So essentially, it seems like the current narrative is that these developments are implicitly encouraging two views that seems consistent to these new results. The first one is that scaling up model and data size improves performance significantly. The second one is that performance improvement transfers to downstream tasks in a desirable way, meaning that it seems like what we're saying as a community is to just have a giant model trained on a lot of data, as much as data that you have, and this is going to work pretty well on any downstream task. An example of one work that I wanted to specifically talk about is that essentially this analysis of which I have a picture here, that essentially they analyze pre-training on ImageNet and then transferring either in fine-tune setting or in few-shot setting to different downstream tasks. And as you could, and so these plots show the downstream accuracy in the y-axis versus ImageNet accuracy, which is the x-axis, and you could see a linear trend. So what the whole story seems to be that there is no saturation in performance. We could just keep increasing performance on our pre-training by scaling up data and model size or compute, and then there is this linear relationship, so you get downstream accuracy as you increase your upstream accuracy. And by upstream, I mean the pre-training data, and downstream is essentially when we take it and do transfer learning, just to make sure we all have the same notation here. But if this was the whole story, of course, I wouldn't be here talking to you about this. There are some important shortcomings about these works, which is that they haven't looked into performance for different choices of hyperparameter values. And essentially, this is an artifact of having limited computational resources. So what mostly has been done is that either we have fixed hyperparameters for all the range of accuracies, or there's been focus since there's been a lot of focus on including on improving state of the art performance. Only they've done hyperparameter tuning on the much better accuracies, and these are essentially impacting the results that we see, impacting that we see this linear relationship. However, when we were to study scaling, we should be concerned about the best performance of model given all possible values for hyperparameters. Another important thing I want to mention is that these plots and these analyses, they look at the limited accuracy range. And again, of course, this can be impact of computational resources or for different reasons. But however, since we have this limited accuracy range in these plots and in these analyses that have been done earlier, essentially there is a caveat that you can't just simply extrapolate these plots without really understanding the dynamics of scaling, and this can lead to incomplete pictures or wrong pictures. In the work that I want to talk to you about today, we do a systematic large-scale study of transferability of essentially models. And what we do is that we investigate the transferability of improvements on a large scale upstream task to a wide range of downstream tasks. And we consider more than 5,500 experiments. These are all on image recognition tasks, and we look at a variety of architectures and the state-of-the-art architectures such as vision transformers, ResNets, and mixers. We have a variety of sizes of these architectures from 10 million to 10 billion parameters, and these are trained on largest scale of available image data, both JFT and also ImageNet 21K, and we have more than 20 downstream tasks that cover a wide range of standard data sets such as VTAP, metadata set, the new Stanford Wiles data set, and medical imaging data set. One disclaimer that I wanted to mention is that we really didn't do all these 5,500 experiments. What we have done is that we've gathered all these networks that different researchers at Google have trained for different purposes, such as improving state of the art, looking at the stability of models, and so on. And we have done the analysis on these. And in the second part of the talk, I'll also talk about some controlled experiments that we have done, but the number of experiments is much less than this. So essentially, we've reused these trained the models that others have trained. We've gathered some measurements from them and have done the analysis. Okay, so what is the setting that we look at? Throughout this talk, we look at these plots that look like this. The y-axis shows you the downstream accuracy, and with the name of the downstream task, which here it's CARS data set, and the x-axis shows the upstream accuracy. And essentially, why do we look at this is because our goal in understanding transfer learning and doing transfer learning is to predict downstream performance for a given model. And in the second part of the talk, I also mentioned why we do this choice of x-axis. But for now, let's stick to it, and then I'll tell you why. So essentially, we look at downstream versus upstream accuracy, and I use the shorthand of DS and US to refer to them. And this horizontal line that you see here is the predicted accuracy as upstream accuracy becomes 1, or essentially reaches its base error. And this prediction comes from a model that we have proposed, that I'll talk about it later in the talk. So this is the setting that we look at. With that, let's move further. Another thing that I wanted to talk about before I get into the results is just let's do a recap of what is a convex hull. And a convex hull of endpoints, A sub j, is essentially a weighted average or linear combination of these points where the coefficients are P sub j's that are non-negative, and sum of them becomes equal to 1. And it's easy to show that, let's say I have a group of models with some accuracies and on upstream and downstream, and let's say I construct a randomized model where whatever input I get with some probability p sub j, I pick model theta j and output the output of theta j on this input. Essentially, this would give me a randomized model, and it's easy to prove that this randomized model will demonstrate the accuracy, which is essentially upper hull of this convex hull that we talked about. But why do I do this recap? Is because in our analysis, we consider the convex hull of the points that we have. And those points are essentially different models that I talked about, these 5,500 models that we know what's the upstream and downstream accuracy is that. And why do we do that? Because is essentially, as you saw in the plot, and I'll show that plot again, there is large variance in downstream versus upstream performance across models. And we essentially have two choices. One is that fit all those the existing points, which essentially fits the average performance, or fit the convex hull, or essentially upper hull of these points, which essentially fits the best performing model. Why is it good to use this? Is because it's robust to the density of the points. It's easy to show that if you look at this upper hull, it doesn't. Essentially, any point in the graph can impact it. So you really don't need to have a lot of points. And if there are sections in the plot that have more density versus less density in other places, this is not impacted by that. And of course, it's really important for practical purposes. Okay, so the first takeaway that I want to talk about is essentially, if you look at these downstream versus upstream plots that I talked about for these more than 20 downstream tasks that we look at, you see this saturation happening as you increase the upstream accuracy by scaling up or by hyperparameter choices. The downstream, and you could look at these horizontal lines, saturates well below accuracy of 1. And you could see there is this nonlinear relationship between the two. And different colors in the plot essentially show different architectures, and different model sizes are shown with different size of the circles. And you could see this is something that's consistently happening. But why is it important that we capture this saturation performance? And it's important because it means that at some point, which I'll get to it mathematically, it does not help you to spend money or compute or data to try to improve upstream performance, because downstream performance will not get better. And this observation is consistent if you change the number of shots in your few shot setting or change your upstream task. So essentially in this plot, the top two ones, which is the magenta and purple, are when you're pre-training on JFD, and the bottom two ones are if you're pre-training with ImageNet 21K. And you could see in all these scenarios, we see this saturation phenomena happening. And we see that for all our downstream tasks. So now that we know there is no linear relationship, we need to essentially model the relationship between downstream and upstream accuracy so that we could predict downstream accuracy. And the model that we propose is this power law model, where E sub ds is essentially the downstream error is such function of upstream error. So E sub upstream is upstream error, and you have K and alpha, which are constants that depend on downstream and upstream and other things. And E sub infinity essentially is your irreducible error, which captures the value of downstream error when upstream error becomes 0 or becomes its base error. And this is essentially, we see 1 minus E sub infinity in our plot. So this is essentially what we use to predict the downstream saturation value. And if you look at the log scaling of plots, which is essentially what people do, this is what shows you that you do not have a linear relationship if you do look at the log scale. And for those of you who are familiar with base error, this is not the base error of downstream task, because it depends on different factors such as what is the pre-training data and size of the shots and so on. So we do some analysis on how do these parameters change when you change the number of shots. And we see that essentially these coefficients correlate with the number of shots that you have in your downstream performance, and correlation values changes if you change the task. So we cannot, even like with this mathematical model, there is no one size fits all. You really need to look at what's your upstream, what's your downstream task, and like what is your number of shots in your few shot setting. One thing that we do is we also look at to look at how well our model fits the data, to look at the prediction error and fitting error by essentially when we have this plot, let's take the last part of it as our validation data and see how the fit works. And essentially we look at it for different downstream and upstream cases and number of shots, and we see that across all of these we have really good really small error in fitting, and especially this works even better when we fit to the upper convex hull or upper hull. And the other thing is that as we have more samples, which in this setting samples means the number of networks that are trained, the error becomes less. However, even if you have small number of networks that are trained, which in this case we use just 100 trained networks and we choose them randomly, our fit is really working well. So essentially for this model to work really well, you really don't need that many samples that we had initially to begin with, and even 100 trained networks, you can use them to fit our power law model that I just talked about and have really low error, so you can predict the downstream performance. Now I wanted to take some time and talk about when we did controlled experiments on this. So now we have some networks that we trained ourselves, and we look into effect of model size, data size, and compute separately. Again, in this plot, we are looking at downstream versus upstream accuracy. The model size change is shown by the color changing, and also we change the amount of data that we have in pre-training, which you could see by the contrast of the values, and also we change the compute time, which you could see it with circle or square or triangle. And what you see, the gray part in the back, is essentially what the data we had when we just plugged in those 5,500 examples that we had from other people who trained their networks. And we could see that we still have the same pattern, and we still have the saturation performance, but we also see that the curves that we end up with are the same, whether or not we change model size, data size, or compute, which essentially tells us that the analysis we did is equivalent to doing a grid search on everything. And the other interesting thing is that here changing these specifically these three dimensions. The examples that we had from the 5,500 trained networks, they also had changed hyperparameters, and you see these variations around this happen specifically due to training hyperparameters such as learning rate schedule, type of different type of regularization use, and so on. Now that we know this, let's investigate why do we have these different trends, and what can we take away from these observation. In order to do this, we overlay the convex hull of ImageNet on all other downstream tasks. So in this plot, ImageNet is the red color, and blue is the other one, which you could see their names on the y-axis. And the two lines, the solid line is for 1-shot setting, and dashed line is for 25-shot settings. And what do we see here? There are two main takeaways, which is that the first one is that the best performing ImageNet models perform very similarly to best performing models in several of downstream tasks, but not for all of them. And also, as the upstream performance increases, the gap between best performing ImageNet models and best performing downstream tasks reduces significantly. So one thing we can see is that, so essentially we cannot find a model that works well across all downstream tasks, or even if they have two models that one of them has better upstream accuracy, it doesn't mean that it has better downstream accuracy. And even if it works better for one downstream, it doesn't mean that it works better for all downstream tasks. So in order to investigate this further, we designed this experiment. So what we do is that, so in this experiment that I'm going to talk about, we have a vision transformer. And what we do is that we move the head to different layers. So what we do is that we chop off the top of the network at different layers and just add a head on top of it. And we look into how this performance changes. So now we have overlaid two plots. The green plot shows that downstream versus upstream performance that we've been seeing. And then the red plot shows what is the performance on downstream if you cut the network at different layers. So you could see the lower x-axis tells you which layer we have put the head on. And you could see these plots have similar trends. And the other interesting thing is that for downstream tasks that saturate faster, higher layers are not needed for better performance. And this aligns with our earlier work and some works from our colleagues, that we have said that lower layers capture lower level features that are more common across different data sets and tasks, whereas fine-grained features reside at top layers in the network. So what it means is that for the tasks that saturate faster, these top layers that are specific to our pre-training or upstream data, these are not needed. These are irrelevant, so we don't really need them. And if you want to take away one sentence from what I've talked to you so far, is that we need data diversity. When we talk about scaling up, we really need to think about a fourth dimension, which is data diversity, because as you could see, this would essentially help with the saturation. Okay, the other thing I wanted to talk about, which is really cool, is that so far I kept talking about improving upstream accuracy may or may not lead to improvement in downstream accuracy. Now I'm going to talk about another case, which is upstream and downstream accuracy are at odds with each other, meaning that if you really want to get better downstream performance, you really need to hurt upstream accuracy. And so let me get into it. So as you recall, when I showed you this plot, I told you that this variation essentially happens due to changing the hyperparameters. So in this analysis that we do for the next part of the talk, we focus specifically of the hyperparameters related to head of our network. Why head? Because when we do pre-training, we discard the head and we put another head that is related to number of classes that we have in the downstream task. So we decouple head from the rest of the network and we change two hyperparameters. One is the weight decay and the other is learning rate. So essentially the weight decay and learning rate of the head are different from the rest of the network, and we play with those. What we see here is, so let me tell you what the plot is. The plot essentially, again, is we look into downstream and upstream accuracy. So downstream accuracy and upstream accuracy are both at vertical axis, and horizontal axis shows the value of head weight decay. And we see that for many of, and the gray shows upstream accuracy, and different colors are essentially downstream accuracy for different number of shots. And we can see that increasing the head weight decay consistently hurts upstream performance, but in some of these data sets, for some ranges, essentially, as you see that, so for example, for like cars and pets, there are these ranges, or even ImageNet, there are these ranges that when you increase the head weight decay, upstream accuracy is getting worse, as I mentioned, but downstream accuracy is getting even better. And so we analyzed this. We looked into why does this happen, and we showed that essentially increasing head weight decay is decreasing the head margin, but is increasing the layer margin at layers that are lower than head. It also decreases the norm of the head, as you could see in these plots that I show here, but increases the layer norm for lower layers. So why do we look into these things? Because essentially, layer margin and layer norm are proxies for the information stored in layers. So what we see here is that when we are increasing the head weight decay, we are pushing the information down from head to layers that are lower than this. So why is, and of course it hurts upstream performance because the head doesn't have that much information to discriminate between different classes. However, since we are pushing the information down, we are reserving this information for the downstream performance. So if a downstream is related to upstream, essentially we're giving it more information, so now it has better performance. And here in this plot, essentially we show the best weight decay for downstream as a function of correlation between upstream and downstream. And this is essentially showing you what I was mentioning, that if your downstream and upstreams are correlated, then pushing the information down from head is essentially going to help your downstream performance. And another interesting thing that you can see in this plot is that there is no weight decay that is optimal for all of these data sets. And so there is no checkpoint. There is no one checkpoint that is optimal for all downstream tasks. So in the first part of the talk, I was telling you that essentially you're looking at the effect of data, but even if you look at the effect of the hyperparameters, even if you fix the data, still there is no hyperparameter setting that is optimal for all downstream tasks. So we need to really stay away from this idea that let's just pre-train a giant network and it's going to work well across every downstream task that you might end up with. One thing that I wanted to mention is that the setting that I kept talking to you about in this, the plots that I showed you, was the few shot setting, but in the paper we looked into, we essentially generalized this to other settings. And what we show is that these investigations and these observations that we had, they generalize when you change the number of shots in your few shot setting. They generalize to the cases when you're in transfer learning setting, meaning that versus few shot setting. So just a recap, when we say transfer setting, when we pre-train the network, we fine-tune the network, the pre-trained network on using this downstream data. However, in few shot setting, what we do is that we just discard the head, put another head, and essentially use the data to just train the head. So we keep the rest of the network fixed. And in both these scenarios, in the paper, we show that these observations generalize. They are similar. Another thing I wanted to mention is that these observations are also consistent across different scaling of plots. So in the community, we use different kinds of scaling when we look at this upstream versus downstream accuracy performance, or when we look into effect of different scaling of different things. We use logit or log or linear. And if you essentially write these plots when you do this change of scaling, still our observations are consistent. And also, these observations are not architecture specific. As I mentioned in the early on, we looked into different types of architectures, ResNet, mixers, and also vision transformers. So in summary, what I talked to you about is a larger scale systematic study that we look into transferability of improvements on pre-training to downstream, or like essentially to downstream tasks. And we observed consistently that we have performance saturation on downstream. It does happen. And even if your upstream accuracy reaches 1, your downstream accuracy will stop way below that. We also model this saturation accuracy, and our model can be used to predict downstream accuracy using that power law that I showed you. And I also showed that even if you have low sample size, meaning that if you have a small number of networks that you've trained and your goal is to fit our model, this model is really robust to number of low sample size. So you really don't need a lot of trained networks. So let's say you have a downstream task that is not, let's say down the road, some other downstream task comes that we haven't captured in our paper. So you can have a small number of networks trained on it, use our model, and predict downstream performance. And essentially, you could see until when it's worth using money or time to try to improve your upstream accuracy, given that the formula that we have. I emphasize again that data diversity matters if you really want to get good performance in transfer learning. And also, I showed in the controlled experiments that it doesn't matter if you scale up your model size, pre-training data size, or compute, they all end up in the same curve. And another thing that we investigated in the paper, but I didn't go into details for sake of time, is that essentially you could just look into upstream performance and look at downstream versus upstream performance. And upstream performance has really high prediction power, and you don't need to look into scaling up these other 3 dimensions, model size, data size, and compute to come up with your curves. Just looking at these, they all show up through upstream performance, and that's enough to be able to predict downstream performance. And also, I talked about the effect of hyperparameters, and I hope that you're convinced that you really need to tune your hyperparameters based on your downstream if you want the best performance for your downstream. And there is no one checkpoint that is the best pre-trained model for all downstream tasks. And I also talked about head hyperparameters and why they're important and how we can use them to help improve downstream performance. So for this analysis, for what I talked about, and a lot more details and a lot more plots, please take a look at our paper with the same name. It's called Exploring the Limits of Large-Scale Pre-Training, and it showed up on arXiv last week. So I want to spend 1 minute and talk about, okay, now we know all these. What's the next step? So I think there are some important questions that we as a community need to look into. One is that we really need to do better uncertainty estimation for the case when the data distribution changes from training to test time, which we call it out of distribution generalization. And also, it would be interesting to look at adaptive architectures for this out of distribution generalization. As I mentioned, for different downstream tasks, not all the network might be needed. And I talked about the effect of hyperparameters. So adaptive training would be something that is interesting. And also, as I mentioned about data diversity, we really need to think more about the data, how to model it, how to ensure data diversity, how do we essentially close the loop. Like, one thing that I would be really excited to see is that if we have a deep neural network model and we understand which parts of the data we really need to go take samples from. So essentially close this loop that, as I show in the schematic in the right. And also, let's say we have a lot of data. How do we know which data to choose? What would be the sequence of the data that we should look at, which is essentially investigating the effect of curriculum learning, that I also have a recent work on it, and please check it out. With that, thank you so much for your time, and I'm happy to take questions.
Fantastic. Thank you, Hanie. We do have 2 questions that have been submitted from the audience. The first is from Ruan. He asks, or she asks, so mainly for DS performance, we need to sacrifice US accuracy?
So it depends. As I showed in the plots, it really depends on your downstream. If it's correlated to your upstream. So for example, let's say it's image, you're pre-training on ImageNet 21K and you want to look at ImageNet performance, these are correlated. So it's good to use this thing that I showed you to play with the hyperparameters to sacrifice upstream accuracy. And so essentially this plot tells you if how helpful it is. So for example, there is this data set that's down here, it's really low, it has low correlation. Then essentially if you it doesn't matter for this one. If you hurt upstream accuracy, still you don't get performance boost. But if they're correlated, it's a good idea to do that.
Terrific. We have this question from Leigh Smith. Since data diversity matters, did you investigate improving US accuracy from incorporation of some of the DS data into the US training case? This would evaluate the benefit. Oh, it's a two-part question. You want to answer that part, and then I'll get the next one.
No, go ahead.
Okay. Then this would evaluate the benefit of expanding the US training set from DS data sets instead of hyperparameter, data size, and model size tuning.
That's a really good question. So one thing that we looked into was that essentially looking into these correlations and also similarity of upstream and downstream accuracy. And we saw, and as I showed some investigations, like when we look at the effect of different layers, and we see that here, when we see that for some downstream tasks, such as essentially like cars or ImageNet, these other last layers are important. It means that this data has been captured. However, if you really want to focus at modeling the data, that's something that I also mentioned in our in the things that I think as a community we need to take care of. Another thing that I wanted to mention, if you want to really plug in those data in this specific setting where we have JFT, then effective curriculum learning is important, and also how much data you have from JFT or ImageNet 21K, and how much samples you have from, let's say, cars that you want to make sure, because essentially they might overwhelm your network. So it's not just a plug-in thing. We really need to think about what would be the sequence of data, what would be the portions. But this is a very intriguing question, and I would be, and I think it needs some scientific investigation to answer, to specifically do that. But my expectation is that it would definitely help, and that's what we're saying in this analysis, that you really need to have data similar to downstream, or not essentially something that you see with human eyes, but in a feature space thing. Because so for some of these data sets, if you look at them, they look similar to ImageNet. They're just images of natural things. However, because there is different ratio of samples and different parts of the distribution that they're capturing, then you see this analysis. So it's more than just looking at data, but there's definitely something intriguing for us as a community to look into.
Great. Thank you, Hanie. When you stop sharing your screen, you'll be able to see the backstage, or you'll be able to see the stage chat. And we do encourage all of our audience to continue to put in questions, direct them to the speaker. They'll be looking at and monitoring the chat throughout the day, and can continue to address any questions that may pop up. And we're getting some great applause here from folks. Great presentation, Hanie. We thank you so much.